In chapter 4, we talk about aqueous reactions and solution stoichiometry. So aqueous reactions is everything that happens in water. Okay, so this is a big chapter. I've split it into 5 sections so that way you do it in small doses and not overwhelm yourself, okay, in this. So this portion is about electrolytes. So let's talk about what a solution is first, okay? And remember, we're talking about aqueous solution. So first of all, a solution is something that's a homogeneous mixture of a solute and a solvent. So remember what homogeneous means. It is something that you cannot tell apart, all right? So which means that the solute is completely soluble in the solvent. The solvent is usually the larger quantity. Solute is smaller. Solute can be liquid or gas. Um, because we are dealing with water, our solvent is always going to be water, which is a liquid, but the solute can be liquid or solid. Okay, it doesn't matter. Gases generally don't dissolve very well in water, so we're not going to be talking about those. Okay, so in any case, when we say we have an aqueous solution, it means that you have a homogeneous mixture and also that it's in water. Now, what happens in solutions, okay, is when you dissolve something in water, that something can dissociate or it may not dissociate. Okay, so I'm going to first talk about this whole thing called dissociation. So dissociation is when something is splitting into two. Okay, so like here, just kind of you're associated and now you are not associated. So that's disassociated. That's kind of what we're talking about. So for example, if you take something like magnesium fluoride, which is shown here, and I can see I have a spelling error here, I will correct that, but in any case, so magnesium fluoride, if you take something like this, and that dissociates in water, then it will give you magnesium 2 plus, which is the ion, and then it will give you the fluoride ion. So before I dissect into all of that, let's talk just a little bit about this equation. All right, so here we have magnesium fluoride and this is in solid. So now in this chapter we're going to have to write all the states, okay, that everything is in. So magnesium fluoride is a solid which is dissolving in water, so which means that now the products are going to be aqueous. Okay, now not everything has to be aqueous, it depends, okay, what we're talking about. So this is aqueous right now, which means that these magnesium ions are dissolved in water. So you have to indicate the state, okay, that everything is in. Now, the other thing that you don't see over here in this equation is water, right? Because you're like, okay, so there's water, but where is it? You don't see that. As soon as you write aqueous, it means automatically that it is dissolved in water, all right? So it's understood that there is water in the background. So magnesium fluoride is dissolving in water to give magnesium 2 plus and 2 fluoride ions. Now the way I've written this equation over here is to show you the red here, which is a subscript. This 2 subscript becomes the coefficient over here on the right hand side. Okay, so it's not that it's MgF2 and there is F2 on the right hand side. It's not F2. Okay, so you're not just kind of pulling this apart into two things. Okay, you're actually dissociating it into ions. Okay, so remember what magnesium fluoride is actually made up of. Magnesium fluoride is made up of magnesium ion, which is Mg2 plus, and then a fluoride, and then another fluoride. That's the two ions that we are talking about over here. That's the 2 indicated here also, right? So when we write the formula, we write it as F2, but when we are writing it as a dissociation equation, you have to write it as 2 being the coefficient, okay? And that's the rule. That's how it works. You can't change that, all right? Now let's talk a little bit about interpreting this equation. So as we did in stoichiometry back when we were talking about moles and whatnot, so here also we need to kind of address that. So here we have magnesium fluoride giving us magnesium and fluoride ions, but when we look at it, how are we looking at it? 1 mole of magnesium fluoride is giving us 1 mole of magnesium ions and 2 moles of fluoride ions. Okay, so even though you have one molecule over here, one molecule, right? MgF2 is just one thing, but it has actually ended up giving us 3 ions because 1 of magnesium and 2 of fluoride. So this is something you have to understand, and it's going to help you. Again, and the only reason I'm teaching you this, well, not the only reason, but I'm mentioning this is because you're going to need this in future, okay, when you do calculations and whatnot. So you're getting 1 mole of magnesium ion and 2 moles of fluoride. So you have a total of 3 ions now. So, and here again, I have just kind of, emphasized to you that don't leave, 2 as a subscript. Make sure that you make it a coefficient. Okay, so this is totally illegal. Okay, you cannot do this. There is absolutely nowhere, unless you're working in a research lab and you make this fleetingly, it's a different thing. But otherwise, there's nothing like F2 minus. Okay, so you have to write the 2 as a coefficient. All right, here. Okay, so then here we go with the products as ions. Okay, so yeah, you have to write all the products as ions only, because when something is dissolved in water, it is dissociated. Okay, again, remember, dissociation means that something that is not associated together. Okay, so it's kind of like, as soon as you dissolve something, the water molecules kind of come in the middle and they kind of separate out the ions. Okay, so here we have strontium phosphate, for example. Strontium is in group number 2, so it's always going to be +2, so make sure you write that as +2. Don't leave it just as strontium. Okay, so this is not going to be strontium plus phosphate. Okay, this is not going to happen, because you need to go ahead and make sure that you put the ions, okay, on there. And then of course, don't forget the subscripts. The subscripts become the coefficients. So here you got the 3, and then of course here you got the 2. Okay, so that's kind of how it works. The polyatomic ions are going to stay as polyatomic ions. Okay, you're not going to dissociate them unless they get dissociated in the equation, in the reaction itself. That's a different thing. Okay, but unless that happens, you leave the polyatomic ion alone as it is. Okay, don't change that. All right, so acids and bases can also dissociate. Okay, what we talked about in the previous slide was not acid and base, it was just, a compound, what we call salts, okay, in general. All right, so but in dissociation of acids and bases, now you're taking an acid and base and then dissociating it. Now we haven't really learned about acids, bases yet, but we are going to, but I need you to understand the concept of it. Okay, so here is HCl, which is hydrochloric acid. Now remember, this is written as AQ. AQ means that it is an acid, it is dissolved in water, which means you're going to call it hydrochloric acid and not hydrogen chloride. Okay, so now HCl, this is already aqueous. Okay, and what is going to happen here is that you're showing the dissociation. Okay, so if you're wondering why did not I write this as HCl like in gas form or solid form, we don't do that for acids. Okay, we will always write acids as aqueous, because one of the things about acids is that they are always acids in water. Okay, which means HCl, as I mentioned to you, HCl can be hydrogen chloride. Hydrogen chloride as a gas is actually not acidic, but as soon as you put it in water, then it becomes an acid. So later on, we're going to talk about acids and bases also, so it will become a little clearer. But here I'm just talking about dissociation. Okay, so when you see acids, go ahead and dissociate them into their proper ions. Write the AQ. If you have H2SO4, again, pay attention to the subscript, okay, and then it becomes 2H+. Now remember, SO4 is a polyatomic ion. You're not supposed to split that up, okay? The polyatomic ion, unless we give you a reaction in which it is dissociating, you don't do anything to the polyatomic ion. Leave it as it is with the charge, okay, on there. So here you only have the 1 sulfate, so here is go, okay, only 1 sulfate. So anyhow, this one we'll talk about later also. When there is only 1 H in the solution, that's a monoprotic acid, and when there are 2, it's called diprotic acid, because acids give protons. Okay, we kind of learned this a little bit back when we were doing nomenclature, but we'll learn more about it. Just be patient. Okay, bases are going to be all hydroxides, and hydroxides can also dissociate. And so if you have something like aluminum hydroxide, then just dissociate it normally, okay, like which is aluminum 3 plus, that is the ion, and then you have 3 hydroxides, okay, in there. So again, 3, which is a subscript, becomes the coefficient, okay, over here. Now in this case, I wrote this as solid. Okay, because aluminum hydroxide is a solid. The difference between the acids and the bases is kind of like that, okay, which is that most of the acids are going to be aqueous and the bases are going to be solids, okay, and then those solids you can dissolve in water. Now aluminum hydroxide, even as a solid, is a base, okay. So for example, I said HCl as a gas is not an acid, but HCl as aqueous is an acid, so it's not the same thing with bases, okay. And this is something you kind of learn as you go on. If you don't remember that, it's all right, you will, okay, eventually it happens, okay, because you use these things all the time, then you know, okay. So you don't have to remember it right now if you don't want to. So again, this is a solid, and then it is dissolved in water and gives ions as an aqueous solution. So a non-metallic base, a non-metallic means there's no metal in there. So that's ammonia, and ammonia with water. So ammonia here is a gas, water is a liquid, and this one is going to give us ammonium ion. So remember, there was only one positive polyatomic ion and then hydroxide in the solution. Now, if you're wondering how the heck did I get this, again, just wait, it's okay. All right, this is an equation that I will give you, so you will not have to worry about how did I form NH4 plus, where did that come from, okay. And I also want to talk just for 10 seconds about this little arrow over here. We are used to these arrows because these arrows mean yield. So you have the reactants and the products. Well, you still have the reactants and the product, but this arrow indicates equilibrium, okay? And equilibrium means that something is going back and forth, okay? I know you're getting dizzy now. So anyway, so it's going back and forth between the reactants and the products, okay? Which means that not all of the reactants are products, and some of the products, they're going back to the reactants, okay? So the reaction keeps going back and forth. That's this arrow. If you see this arrow anywhere, that means dissociation is not complete. This kind of an arrow means the dissociation is complete. An equilibrium arrow means dissociation is incomplete, okay? And that's an important thing coming later on. So here are the strong acids and strong bases. So the reason I gave you this over here is because they dissociate completely, okay? And right now you need to know these things, okay, as to what is going to dissociate completely and what does not, because coming forth, we're going to have to talk about this, okay? So strong acids and bases, they will dissociate completely. The only base that we have talked about that did not dissociate completely was the ammonia, okay? That was the only one so far. Okay, so here is just writing dissociation equations, and I really like to get you all started with writing equations for dissociation first, okay? Because I need you to understand how the dissociation works. Once you understand that, again, this is the foundation that I work on, okay? And then later on things will become easier for you. That's my goal, right? So that I teach you in certain way that you can learn, later on things a little bit easier, okay? So now when you're looking at how things are working and what is dissociating, what is not dissociating, so when you look at something like, C2H5OH, okay, for these compounds, so covalent compounds do not dissociate. Why don't they dissociate? They don't have any ions in them, okay? So they do not dissociate. Only anything that has ions, that's going to dissociate, okay, first of all. So C2H5OH is not going to dissociate. Then barium nitrate, that is going to dissociate. Do you see how I said C2H5OH? Because this is kind of like organic chemistry, and I have not taught you the naming of any kind of organic substance, so I'm not even naming it for you. Otherwise, this is actually ethanol, okay? This is alcohol, but I'm not naming it because we haven't learned it. But barium nitrate, and barium nitrate will dissociate in water because it's an ionic substance, okay? CH3, again, an organic substance, is all covalent, will not dissociate, which means what am I asking you to do right now? Do you see that? I'm just asking you to classify things as ionic or covalent, which you should have already known by now. And you should be able to classify that without any problem. Okay, so you see baby steps. All right, so once you know something is covalent, it's not going to dissociate. Once you know something is ionic, it is going to dissociate. Once you are able to identify what's going to dissociate, then we're going to write the equation for it. Okay, so again, step by step. Water. So water dissociates? No, water does not dissociate. Water is a covalent compound. Okay, it does not dissociate. So here is one thing, okay, about some of these things that we are learning right now. Okay, remember this may be your first chemistry course that you're taking. So if this is the first one, remember I have to teach you a lot of basic stuff. Things change later on, okay? As you learn more and more about chemistry, some of these things are going to change, and I don't want you to come back to me and say, oh my God, you didn't teach me this. It's not that. It's just that, you know, once you become a little bit more settled in chemistry, then I can teach you something more, or you can learn something more, okay? That's how it works. So, and I'm saying this because things will change, okay? And this chapter, the aqueous reaction chapter, what we are doing over here is kind of like one snowflake in a blizzard, okay, of snow. So it's a very small thing that we're doing right now, okay? So just be patient with yourself and be patient with me. So here's water. Water will not dissociate because it is just all covalent. Copper 2 sulfate, yes, that will dissociate because it is all ionic substance. Okay, so the second question is write the dissociation equation. And so here we go. Okay, here are the dissociation equations. Barium nitrate, you have one barium and then two nitrate ions. Copper sulfate is copper 2 plus and sulfate, just 1-to-1 ratio. Here barium is 1 and then nitrate, there are two nitrates in there. Okay, so that's kind of keep it simple that way. All right, so now once you know dissociation, now I can explain a little bit about electrolytes to you. Sometimes, you know, different teachers do it differently. I like to talk about dissociation first, and then I talk about electrolytes. So electrolytes is anything that conducts electricity, any substance. It could be aqueous, not aqueous, it doesn't matter, but it's any substance that conducts electricity. Okay, so I hope you like that. I had AI make this for me. I told it to make a beaker, but it made a flask, but that's okay. It looks pretty, doesn't it? Anyhow, okay, so any substance that conducts electricity is considered to be an electrolyte. All right, so there are three kinds of electrolytes that we say. So there's a strong electrolyte, weak, and non. So strong electrolyte, as you can tell by the word, is it's something that conducts electricity really very well. Okay, weak electrolyte does not conduct electricity very well, and non does not conduct at all. So that is your first classification that you need to understand. The second thing you need to understand is why that is happening. Okay, so the strong electrolyte, the reason it's conducting electricity is because there is 100% dissociation of whatever is in the solution. What is dissociating? Only ionic substances, right? So that's what I talk about dissociation first. So now you understand that whatever can dissociate will be an electrolyte, strong acids, strong bases. Okay, so you already know about this. So you know that anything that dissociates completely is going to be a strong electrolyte. Anything that does not dissociate completely is going to be a weak electrolyte. Anything that does not dissociate at all is not going to be an electrolyte. So that's a non-electrolyte. Now things become a little easier for you. I hope so. Okay, so strong electrolyte, again, anything that will dissociate completely, which is ionic substances. Weak electrolytes, so remember we talked about ammonia, which was going back and forth, back and forth. Yeah, again, I'm making you dizzy. So back and forth again. So anywhere you see equilibrium, that means things are not completely dissociated. Okay, so in those cases, then you're going to have a weak electrolyte, and a non-electrolyte would then be a covalent compound like the alcohol, right, that we just mentioned before. So a covalent compound cannot conduct any electricity because there are no ions. Okay, remember what conducts electricity is the negative ions that we have in solution. Now the positive is there, because you just can't have a solution of negative ions. So you have to have positive with negative, okay, in there. So the positive don't conduct electricity. It's actually the negative ions that are conducting electricity. So that's what you need. So non-electrolytes don't have those ions, okay, in there. So that's electrolytes for you. So here is a little bit of a pictorial, okay, to help you know this is not AI. This is something that I drew myself. And so here a strong electrolyte will have a big aura, you know, bright bulb shining when you put electrodes in the solution. And here, and you can see my demo on this one, okay? So I have a video and you can see that video which shows you all these electrolytes in there. So a weak electrolyte has a little bit of a weaker halo, and then the non-electrolyte, absolutely nothing. The bulb does not even light up, okay? So you don't really have any light coming out. So that's kind of what electrolytes do. And what you do actually is you make this contraption, okay, and then you stick the electrodes in the solution. The thing about aqueous solutions is that they're homogeneous, right? Which means that if you have salt dissolved in water or sugar dissolved in water, it still looks like water, because both of those substances, when they dissolve in water, they still give you a clear colorless solution. Okay, so you can't tell unless you taste it. And you know, we're not supposed to taste things in chemistry. Well, depending on where you're working, okay, but chemistry labs, you're not supposed to taste anything. So how do you know that if you have something dissolved in that water or not? You know, are you going to trust that beaker, or are you going to say, oh my God, there is something in there? So the first thing you can do is stick electrodes in there, okay, and see if your bulb lights up. Now, if it lights up, it means there is definitely something dissolved in it. If it doesn't light up, doesn't mean that you don't have anything dissolved in it. It is just that it's a non-electrolyte. Okay, so at that point, you may want to do some other test to figure out if there is anything in the water. So for example, if there was any alcohol dissolved in the water, it's going to be a non-electrolyte, but you still have alcohol dissolved in water. So it's not pure water still. Okay, so you see what I mean? But the simplest test to see if you have anything dissolved in there is just to go ahead and stick electrodes and then see what happens. Okay, so it's a very simple test. Okay, so practical applications of electrolytes it's too many. Okay, it's too many. First of all, our body is made up of a lot of electrolytes. So we have a lot of ions in our body, which help to maintain so many functions: blood pressure, pH, the acidity in our body, the lungs, all, you know, the whole equilibrium in the lung system is all you know, ions that maintain that. Okay, so read this up. It just tells you a little bit about how our body is completely dependent on electrolytes. Okay, and athletes will know this really well, is that, you know, when you exercise outside in the sun, you're running outside, you know, you're going for long runs and whatnot, you know, you sweat a lot. When you sweat, you first of all have to hydrate. You know, any person will know these days, you know, everybody carries their bottles with them, so you all have water. Okay, so everybody knows the benefit of hydrating. But if you lose too much sweat, then you also lose electrolytes in that sweat. Okay, and so you have to replenish those electrolytes. And so the best way to do that is to drink some electrolytes. Okay, and University of Florida was the one who made the first electrolyte Gatorade, because their athletes were, you know, kind of getting sick, and so they're like, okay, we need to figure what's going on. And so I think it was the coach's wife, the football coach's wife, who came up with the solution, you know, for having electrolytes, you know, in solution. Yeah, they say chemists have all the solutions, right? Okay, that was my chemistry joke. But anyhow, so Gatorade is nothing but, you know, electrolytes. Okay, the only thing you have to do is you have to give it good flavor. So remember Gatorade, Gators, all right, you got it? Yeah, Florida connection. Okay, so read about it. It's really quite interesting. Okay, the history of electrolytes also. And we do it, you know, when we get dehydrated, the best thing to do is go ahead and get some electrolytes. Okay, so here's another question about classifying compounds into strong or weak electrolytes. So all you need to do now, okay, now you've done dissociation. So when you look at these compounds, all you have to do is see, okay, are these ionic, covalent, or something in the middle? all right? Because if something is going to be ionic, then yes, it's going to dissociate. Okay, close your eyes and say it's going to dissociate. If it's going to be an acid, strong base, completely going to dissociate. It's going to be a strong electrolyte. If something is a molecule, which means covalent, then make sure that it is covalent and not an acid, okay? Because acids are also covalent, right? HCl and stuff like that. So those are all considered to be strong electrolytes, okay? Now these are all going to be solutions in water, all right? So don't think that this is going to be just by itself. These are all solutions in water. So what is HBr? HBr is going to be strong electrolyte because it's an acid. Okay, KCl is going to be a strong electrolyte because it's an ionic substance. HI is hydroiodic acid, so that's going to be a strong electrolyte. Hydrogen, no, because hydrogen is a covalent compound, so non-electrolyte, right? So the KOH is a strong base. Yes, it's going to be an electrolyte. Okay, and then NH4I, which is ammonium iodide, that's going to be a good electrolyte as well. And then HCOH is a weak electrolyte because it's a weak acid. So I will give you a list of weak acids and weak bases, and I just need you to remember those. Okay, so you don't have to worry about saying like, you know, oh my God, if I see this on the exam, what is it going to be? You don't have to memorize all of them, but I'm only going to give you one or two, okay, of the weak electrolytes. That's probably going to be the most challenging one for you, okay? All the others are going to be easy, okay? So the weak electrolyte sometimes is like, is it weak? I don't know. Okay, but anyhow, all right, so that's the electrolyte strengths for us to dissociation and all that. So that's all I have for you in this little section.